Okay. One last thing we want to say about finite difference is that it's trivial. It's almost trivial to generalize what we have learned to a nonlinear partial differential equations. Nowadays, I think you study you probably didn't really study any partial differential equation in analytic sense, right? Did you take any classes that actually does pure mathematics on partial differential equations? I mean, if you haven't, a statement like this is almost trivial, right? But if you actually use the analytical methods to study partial differential equations, you're gonna know like how much harder it is to do any nonlinear stuff with just the pure math in partial differential equations. So I actually studied math in my undergrad, and partial differential equation is actually the single most disappointing class I took in my whole undergrad. The reason is the following: when I took the previous class, ordinary differential equations, I actually learned a lot. So there is a lot of things you can do even without numerical methods, right? I mean, you can really do a lot on ODEs even without numerical methods. I mean, a lot of things you can only analyze qualitatively without numerical methods, especially for very nonlinear ODEs. But you can still study a lot of things even without quantitatively. You can study a lot of things qualitatively. When we go to partial differential equations, I expect to learn as much. But the thing is that you can only, with pure math, you can do so little to so few partial differential equations. It's utterly disappointing, right? I mean, like what you learned, the methods are totally not generalizable. It's just to work on that single equation. And anytime you introduce any kind of nonlinearity, anything you learned is not applicable anymore. So the good thing about numerical methods is that it generalizes really naturally to nonlinear differential equations. So for example, I'm going to introduce a slightly different equation as we have looked at before, du dt plus now u times du dx equal to 0. Okay, so what did I change to what we studied before? We studied du dt plus a times du dt equal to 0, right? Now I have u times du dt. I replaced a, which is a constant, with u, which is an unknown solution. Okay, it looks like the equation is as simple, but the thing is, this equation is not linear anymore. How do you know this? You know this because if I have a solution u to this equation, I double the solution. I plug in 2u into the equation. Is the equation satisfied anymore? No, because this term is scaled by 2, this term is scaled by 4, right? If the previous equation is satisfied and it's not trivial, it's not u equal to 0, then definitely the new solution would not satisfy the equation if I double it. So it's not linear. And this equation is actually a prototype equation for a lot of the nonlinear phenomenon we see in a lot of physical phenomena like shock waves. Okay, actually, this equation models shock waves amazingly well, and it is actually the equation to solve. I mean, there is gonna be coefficients on this. It's not but this is a scaled version of this equation. Is actually the equation to solve if you want to propagate a sonic boom from a supersonic airplane down to the ground. Actually, solving this equation, given the initial condition, which is the pressure distribution around the airplane, right? That has to be computed by solving the actual Navier-Stokes equations. But if you know the pressure distribution near the airplane, then this equation is going to tell you how the pressure distribution is going to look like on the ground. Okay, and you probably know, like NASA is building a quiet supersonic airplane demonstrator that is supposed to fly around the United States and collect data on how people perceive this quiet quiet boom, right? So how do you design this kind of airplane is quite interesting. You first you have to be able to predict, right? You have to solve the Navier-Stokes equations around the airplane to figure out what's the pressure distribution around the airplane. But it's totally computationally infeasible to solve the Navier-Stokes equations in a domain that spans all the way from the airplane to the ground, right? That's just too big of a volume to solve a three-dimensional partial differential equation. You need too many grid points. So this equation is called the Burger's equation. Is actually what we solve. There are coefficients because at different altitude, the temperature is different, the density is different. So it's this equation is going to be a little bit different going from a high altitude to the ground. But this is the equation to solve to propagate the shock wave. And when you hear it in the ground, it's still a shock wave, although it's much weaker. It's on the it's a very weak shock wave, right? So